So today's lecture is about quantum walks. So a bit less mysterious than Tuesday's title, but it connects in different ways to Tuesday's talk. So let me try to introduce what they are, but before doing that, let's talk about the classical version of this. Right? The quantum walks are in fact the quantum analog of what we call random walks. And random walks are already quite a bit less scary. So we'll talk about quantum walks first, random walks first a little bit, to get some intuition about what's going on. It's going to be a bit graph theory and things like that. So you should all be sort of feeling very comfortable. So okay, what's a random walk? So let me start by describing what a random walk is. So we imagine, so I always draw a graph like a circle, but it doesn't make much sense because, in fact, then I'll do this. So, but you imagine there's some state space. So I have a graph, we have a bunch of vertices, V, which you imagine as being a big block of states, and then there's some edges between these vertices. And in fact, I'll assume that this graph is, and this will be for the better, I'll assume that is regular, deregular in particular. So this one is not deregular, and it's not so easy to make it deregular, so I'm not going to try. So deregular just means that every vertex has the same number of neighbors, right? So let's say 5 neighbors or more than that. And that's going to make things a bit easier. Because what I'm introducing next, this random walk, we'll think about it as a Markov chain or a random process, which I'll denote xt for t greater than or equal to 0. And what that looks like is pretty simple. You have some initial vertex x0. Now x0 could be distributed according to some distribution. And then it just jumps to uniformly random neighbors. So it has d neighbors, so it'll jump to, say, this one, and jumps to this one, maybe back to this one, then this one, and so on. And after t steps, that's what we call xt. Okay, so this is not so hard, right? You can just imagine doing that. You can imagine implementing or being a random walk, right? If you randomly walk around on a map or something, and you're essentially doing that, right? So I want you to keep that in mind. But the way we describe it is a bit different, because we describe it using linear algebra. At least that's what I'll do, because that connects better to quantum walks. So specifically, what we do to define this random walk using linear algebra, we define this thing called a transition matrix, which is going to be a stochastic matrix. So it's a transition matrix. I will denote that by P. So assuming that we have something like n vertices, this will be an n by n matrix, a real valued matrix. In fact, in this particular case, all its entries will either be 0 or 1 over d, right? More specifically, it's completely defined by saying that Pij is 1 over d if ij forms an edge. So the transition probability, there's always an ambiguity of how to read this, but let's read it from left to right. The probability of jumping here at vertex I was the probability of jumping to vertex j is exactly 1 over d if j is a neighbor. It's going to be 0 otherwise. Okay, so if d is constant, then this would be a pretty sparse matrix. And it's useful because we can easily use it to describe given the distribution of the initial vertex, what is the distribution after t steps of the walk? In particular, the stochastic transition matrix is set up in such a way that if this initial vertex x0, so I mentioned that it could be distributed according to some distribution. So let's say it's distributed according to distribution p0. So this is again a distribution over these n vertices. Then xt will be distributed according to, we define it, it's distributed according to some distribution pt. But this distribution will exactly be equal to p to the power t applied to p0. So I want to stress this a little bit because this seems like a non-trivial operation, right? It seems like, I mean, we were talking yesterday about applying these in quantum linear algebra and so on, and being able to manipulate, huge matrices and so on. And there's always a bit of a twist to that, you're not, it's a very different thing from actually writing down the thing and manipulating that, right? We're kind of doing it in an online fashion if you want. And similarly, doing just one random walk step on some very simple and trivial graph, in fact, can be described as if you're applying this huge, random walk transition matrix to some probability distribution, right? But this is just the way we describe things. It shouldn't, it shouldn't confuse you, right? There were some people asking about, in fact, I'll come back to it but I was talking about some eigenvalue decomposition, and then you did some operations there, and there was some confusion whether we actually had to compute this eigenvalue decomposition and so on. And we do not, right? It's typically just a sort of way of describing what's going on. Okay, so is that okay so far? Yeah, okay. So what can we say about these dynamics now, right? So we want to kind of understand if we take a sufficiently large number of steps, what's going to happen. And in fact, under mild conditions, namely, if this graph G is irreducible, meaning I cannot sort of split the graph in two without breaking an edge. So from any vertex, you can go to any other vertex. And this is more of a technical condition, just again, to make our life easier. It's non-bipartite. And by non-bipartite, I mean, this is what you call a bipartite graph, right? A graph where you can kind of split the vertex set into two sets so that there's only edges going from one set to the other, but not within the set. You can kind of see what the problem is here in the sense that already spoiled that we want this thing to converge, but here it would not, right? Because if we start on this side, then at all even steps, we're always going to be back on this side. At all odd steps, we're always going to be on that side. So this kind of does not converge to the thing that we'd like to, which is the stationary distribution. So if G is irreducible and non-bipartite, then you can show, and this is kind of the starting point of a lot of these tools, that as t goes to infinity, we converge to some stationary limit distribution, which we denote pi. Okay, so this is maybe not so special, but okay, what's good is that this holds for any initial distribution p0, right? So in particular, it holds for any initial vertex that you would start from. So somehow, wherever you started, as t goes to infinity, you'll always look at the distribution or how you're distributed across the graph. It'll always be the same distribution, in particular this distribution pi. And I said I made the graph regular to make our life a bit easier, and in fact, it already does, because this will be uniform provided the graph is regular. And that's exactly what you're going to be assuming throughout. Okay. So this is not only the limit distribution, I also call it the stationary distribution. in the sense that if you start in a stationary distribution, then you're going to stay in the stationary distribution, right? Because for this to be a limit distribution for P, should mean that after we converge, if we again apply P, then we should stay in pi, right? We should kind of stay in pi forever. That's also why we call it the stationary distribution as well, in the sense that we would have started from pi distribution in some way, in some sense, would not change the stationary distribution. Okay. So this is kind of the sort of existence and limit statement, but as an algorithmist, you want to kind of quantify exactly when this will happen, right? Maybe I can already reveal a little bit, maybe why we like this to happen is because often there's many interesting sampling problems to solve, right? There's many problems that you can solve through sampling. There's these entire areas of Markov chain Monte Carlo in statistical physics and so on. People really often care about sampling from some Gibbs ensemble or some distribution that is otherwise hard to describe, but then often it's easier to describe some sort of Markov chain that converges to this stationary distribution. Now here, as I said, just to make things easy, it's kind of the uniform distribution. So you might say, okay, this is not very interesting, but in general, you'll be sampling from more convoluted distributions. Okay, and so with that in mind, the fact that sometimes we kind of want to sample from the stationary distribution, we want to kind of set up a Markov chain to do that. You can ask yourself, how efficiently can we actually do it? And that brings us to the next term, which is the mixing time somehow. So you really want to think about this as, sort of in the worst case, your initial vertex is not distributed across, just deterministically starting from some point. And then you'll see that as time evolves, this distribution, this PT, kind of starts mixing across the graph, right? So you can kind of visualize that if you want. And this mixing time is one of the key notions when you talk about, random walks and Markov chains and applications of them. And what you can kind of prove it is not so hard to prove. And the intuition is a bit similar to, why the spectral gap showed up on Tuesday as well. For a random walk, you can think about this pi as being somehow the ground state of the random walk, right? And in that sense, if we sort of set out the spectrum of this random walk transition matrix P, so again, as I said before, we want to kind of deal with this in a linear algebraic fashion. Then, so this is the spectrum of P. Then let's see where we have some eigenvalues, right? So I just said that pi is a stationary distribution in the sense that it's fixated by P, right? So if we apply P to pi, we again get pi. So that means that we have this. The P will also be symmetric and perfectly well behaved, so we'll have real eigenvalues, and in fact we'll have one real eigenvalue equal to 1, because this precisely corresponds to the stationary distribution. And in fact, you can even show this is the unique eigenvalue 1 eigenvector. Okay, under these conditions. And then by sort of, you can do it by linear algebra, there's different arguments, but in a sense, it's not too hard to prove that then all the other eigenvalues are going to be between -1 and 1. In fact, strictly between -1 and 1. And how strict it is between -1 and 1 is exactly what you're interested in. Because this here is kind of what we'll call the spectral gap. Like we have this one eigenvalue that we really care about. We'd like to go, like for all the other eigenvalues to kind of go away in a sense. So what we do is we kind of say that this thing here is completely contained within sort of 1 minus delta and -1 plus delta. So in this case, we don't just care about the gap around 1. For technical reason, we also care about the gap around -1. But this is a technical condition. You can always, in fact, deal with if there's an eigenvalue close to -1, you can always kind of get rid of that. So what you see is that we have the spectrum and we have the spectral gap. And now you can already feel what I'm going to say next, namely the mixing time or sort of the convergence time of this random walk will scale with the inverse of the spectral gap. Okay, so the larger this gap is going to be, the faster this thing is going to converge. The smaller it is, the slower it's going to converge. Okay, so let me give a couple of examples to get some intuition of what's going on. Maybe it could also help that to clarify why you care about particularly this gap. What you can do is, maybe I can just do it on this chunk here. What you can always do is you can kind of say that P0 has a spectral decomposition into eigenvectors of P, right? Let's say it's some alpha, J, and okay, I'm going to use a cat here, but it's just a vector, right? Just an eigenvector. You can kind of decompose it into these eigenvectors such that if we apply P t times to 0, we'll get something like sum alpha j lambda j to the t vj, okay? And we know we'll have some projection onto the stationary, which corresponds to sort of, let's call it the 0 eigenvector with eigenvalue 1. So this will be equal to pi plus some alpha j lambda j to the t vj, for now j larger than 0. And these lambda j's are exactly these here, right? This would be lambda j, and this would be lambda 0. And this one corresponds to the stationary, this corresponds to all the other eigenvectors that are in the spectral decomposition of P. And now you can kind of clearly see that as t goes to infinity, this thing doesn't change, right? Because we had a lambda j equal to 1 here. But this thing will kind of start shrinking, right? As t goes to infinity, all these eigenvalues, if you kind of take powers of them, they kind of converge to 0. And exactly how fast do they do that? That exactly depends on the gap here. Specifically, if you want this to be appreciably small with some guarantee, then we want to take t something like 1 over delta. And that's exactly kind of the spectral or linear algebraic intuition here. Okay. Any questions so far? Yes.
So here pi is actually all this, so this alpha 0, lambda 0, t v0.
Yes, with lambda 0 being 1.
What is the physical intuition behind this?
The physical intuition with, so this is a spectral decomposition, right? And I don't think there's necessarily a physical intuition. It's just a way of describing kind of this, you can think about it as this dissipative dynamics, kind of a contrast with quantum dynamics, where in quantum things kind of rotate around and never go away. But classically you do, because even after taking a single step on a graph, you could already have forgotten where you started. And you can't have that with quantum, but you can have it with classical stuff, like the stochastic stuff. And this is kind of reflected by having these eigenvalues that kind of die out. Is that helpful? Not, no?
I have to think more about it. Actually, I have seen something like that regarding something in field theory, where they are also taking out the 0th term separately and calling this classical and the rest as the quantness. So
Okay.
just trying to figure out if there is an answer.
In the chat, David Wierig points out that there seems to be an alpha naught missing in front of the stationary distribution.
So I was being a bit, let's say, pedagogic about it. So what I hid is, like, and then this is a bit of a calculation that, it's kind of a bit insightful. So in fact, the 0th eigenvector, so we have alpha 0 equal to 0, equal to 1, and we have V0 equal to the uniform distribution. But I mean, we're looking at a spectral decomposition, so we want to have something normalized. So it's 1 over square root n sum I, right, where I is like the set of vertices of the graph. And then you get that this term here corresponds to somehow the projection of your initial probability vector onto the stationary state. And what you can show, so I'm not gonna, it's 2 lines, so maybe it's a nice exercise. What you can show is that in the spectral decomposition, if you have something like alpha 0, V0, V0, like the projector, and you apply that to some initial distribution P0, I mean, I know this is blasphemy, right? Like there's a probability vector here and a ket and so on, but let's, you know, let's just do that. Then what you can see is that this will exactly be equal to pi. So like be exactly equal to the. Oh, sorry. Yeah, lambda 0, right? Exactly. This is lambda 0, and you know, lambda 0 to the t. Projector on V0 is exactly kind of what we want to put in front here, and this will just be equal to pi. Okay.
How can we interpret the so the eigenvector with eigenvalue 1 is the uniform distribution, okay, but the others are not probability distribution, right? There are some 0 things. How can we interpret them? Like
you don't like. I mean, this is kind of what I'm very happy with this question, because this is also what I want to stress a little bit, is that somehow here you can't do anything, you know, wrong, right? You can't pick up a sign all of a sudden, right? Like everything is going to be non-negative, like however, you know, your xt is distributed, is going to be a non-negative thing and going to behave well. Then somehow it's kind of interesting that to then try to understand that how, like somehow these but this has to be the case, these eigenvectors have to somehow, you know, sort of collaborate to always have a proper, you know, probability distribution. But they do. Like, I mean, they have to do that because, I mean, this is exactly well behaved, so this has to be. But it's a bit counterintuitive to I think I agree to look at that picture, and then you have all these eigenvectors, and it doesn't connect to, you know, any distribution or anything. And I think that's maybe a bit of the downside of looking at this in an algebraic manner. I think there's other ways to do it, but this connects best with the quantum also.
So why do I get this? So when I multiply, or when I project P0 onto the uniform distribution, why do I always get the stationary distribution from this? It seems like I would always get a different value depending on my P0.
Okay, so we can do it, right? So lambda 0 is 1, so this thing drops out. V0 is this thing, right? And so let's pick out, you know, the 1 over square root n, put it in front, also pick it from here, so we'll get 1 over n, and then we'll have some I, right? Now this thing here is pi, and then the second one, if we expand that, we'll get some, say, j applied to P0. But this here is exactly the all ones vector transpose, right? And if you take this inner product, given that the entries of P0 sum to 1, this will be exactly 1, and so we just get pi.
So pi is always the uniform distribution?
So it is, because I'm assuming that the graph is regular.
Oh, okay.
Because also then the matrix is symmetric, and you have like a nice spectral decomposition and so on. And you know, you can do everything without this assumption, but it's just more messy. Okay. Now let me just put down some kind of examples to get some insight into this, you know, spectral gap business and so on. So let's look at some examples. Right? So one of them is the complete graph. So it looks a bit like this. Say we have a bunch of vertices, and now just put all the edges that you can kind of come up with, which I think I did. So exactly right. So what do you think? Like, let's say, you know, what do you think about the spectral gap of this graph, for instance? If we look at a random walk on this graph, we look at this transition matrix, what can we say about the spectral gap? Sorry? Exactly. And in fact, if you design it in the right manner, then the spectral gap will be even equal to 1. Exactly. It's not completely trivial, because normally you would in one step, you know, jump to all your neighbors, which is not exactly because the right distribution, because it's, you know, uniform over n-1 vertices. But then if you kind of hack it a little bit and you add a self group or something, then in fact, in one step, you are distributed according to this uniform distribution. So we get here that this spectral gap is approximately equal to 1. Then let's look at another object, which I'll call an expander. And we start, constructing it very similarly, but now instead of adding this, dense amount of edges, we just give it, every vertex like a random number of like a constant number of random neighbors. Now, what do you think the spectral gap is of this one? So there's not a, I mean, it's a very hard question, in fact, because what you can prove is that this thing will actually behave exactly like the complete graph. It will actually have a large spectral gap as well, which is kind of remarkable because this is a very trivial graph, right? Whereas this is not. And this sort of expander graphs, which are very sparse graphs, but they are extremely well connected. You kind of, if you take a couple of steps, you'll essentially be completely lost inside the state space. They're, extremely useful objects throughout CS and maths and coding and everything. And it's nice, you can connect it to random walks. And then now the last one is a cycle graph, where again, I start in the same manner. I have these things and I stop. That's all. This is the graph. Let's say that we have n vertices here in a cycle. Anybody have some intuition or a gist of what the spectral gap would be? Could help you think about what do you expect that the mixing time is on a graph like that if you do a random walk. 1 over? So 1 over n would mean that the mixing time scales with n, right? Now you have n vertices here. Now what's going to happen if you do a random walk on this thing? Exactly, right? You can kind of fold it open and think about it as a line if you want. And if you do a random walk on the line, you get this diffusion. And in n steps, you'll only spread like a distance square with n essentially. So you need n squared steps here, kind of spread across this graph. And in fact, you can indeed prove this is much easier than this one, in fact, that the spectral gap is something 1 over n squared. And so after something like n squared steps, you'll be kind of, mixed. And this is interesting because it seems like a simple graph, but then the mixing time is actually very bad. Typically in applications, you care about mixing times that are polylogarithmic in the size of the graph, much like you can get with expanders. And so cycle is kind of an example of a very bad graph in that sense.
How do you look at a graph and decide upon a spectral gap? I could not quite understand.
Sorry, say that again?
So how do you look at a graph and just decide like what is the
what the
spectral
intuition
gap?
is?
Yeah.
Okay, so that's a very good question. So there's one very nice picture. It's called Cheeger's inequality, and it gives you a very good a grip on what's going to be the spectral gap. In fact, what you want to avoid is sparse cuts in the graph. Now, what's a sparse cut? A sparse cut is if your graph is not connected, then it's never going to mix, right? So there's like one extremal case. Now, if you're, not connected, you are connected, but barely. Like, let's say that you have two complete graphs, but they're connected by a single edge, and you have this very sparse cut here, right? You can kind of just remove very little edges and make the graph disconnected. And you can quantify that using the expansion of the graph. And you can directly link the spectral gap up to there's some quadratic gap there to the expansion of a graph, right? Like here, you think about it, like here, there's no sparse cut, right? There's no way that like if you take like a random cut here, then because these edges are chosen randomly, you'll actually have massive amount of edges crossing that cut. But here, this is not the case, right? However you kind of pick your cut, there's just two edges that cross it. And you can kind of separate n over 2 and n over 2 vertices by just chopping off two edges. And that means there's a very bad expansion. means it has a very small spectral gap. Okay, any other questions? Okay, if not, let's talk about sort of dual quantity, which we call the hitting time. And I call this a dual quantity because what we want to do in mixing is, we start from a vertex like x0, and we kind of want to mix, we want to sort of go to this uniform distribution. So we want to spread out. Now, and the hitting time is kind of the exact opposite picture, where you imagine that you start from, let's say, the stationary, but you want to find one element. You want to converge to one element in the sense that whenever you encounter it, you're going to stop. Like when you hit the element, you're going to stop. So let me just draw it. So again, we have this blob, and then we have a bunch of vertices. And let's say that we call this the set M, like the sink or the set of marked vertices. And we start from some random walk here. And now this x0 could have been, like, let's see, we could even assume that it was distributed according to the stationary distribution, right? Then we're going to sort of jump around on this graph, and we can ask ourselves the question, like, what is the time that we hit this set? And when we hit it, we stop, right? And so in this case, you're kind of going from the stationary distribution, which is all around, to a small set. So it's dual to that picture. And then we can define this mixing time as tau m is a random variable, and it equals the shortest, the smallest. Sorry, there should be a min here. The shortest t such that xt is marked. And we'll assume that x0 was distributed according to pi. Like you start from a completely random place in the graph, and you're asking how long does it take me to hit this set M, right? This is a random variable. This is what we call the hitting time. Now, with some abuse of terminology, we'll also call the expectation of this thing, which is no longer a random variable. It's just a quantity that we associate to the graph, and it's a function of M. This is what, we'll actually call the hitting time.
That's terrible abuse of notation.
There's 3 hitting times here, right? Yeah. But I mean, how would you do it? I think it makes sense to call the expectation the hitting time, just like you call the mixing time sort of the, but then it's a random variable, so. Yeah, I was not gonna burn myself today, but look at that. So, okay, so there's that. There's the hitting time. So let me ask a question now. What if we take a complete graph and we mark a set of elements M, and we wonder, what is the hitting time on the complete graph? So does anybody have a hunch?
Like, I don't know if I understand the definition properly, so probably this will be the way to test. I mean, is it a minimal time when basically there is any chance at all that you arrive at that point starting from some point, or no?
No, so
what is this minimum?
So this minimum is defined with respect to an actual trajectory, right? So there's a very well-defined point where you're going to hit the time, hit the set M, but it's going to be a random variable, right? It's going to depend on the particular trajectory, which is a random trajectory. But then you look at the expectation, then it's kind of a, yeah. Yes?
It should be like M over N, if M is the number of elements that I'm looking for and N the number of total elements, because in each step I'm just getting a random element.
So you're saying it is?
M over N. M is like the number, the size of the set M that I'm looking for, and N
So it's you know,
Well, n over the other way around.
exactly right. So
Sorry.
the thing is that in some sense, after every step, you know, you're kind of again distributed uniformly, right? So someone you can imagine in every step, you kind of draw a random sample from the stationary distribution, which is the uniform distribution. So this random walk effectively samples, you know, uniformly random elements from the full set in every single step. And given that there's m marked elements and there's a universe or a state space of n vertices, you'll get that this is exactly like, you know, put of the order n over m, right? And in fact, slightly more insightful is, you know, calling this exactly 1 over the sort of probability that you'll hit a marked element if you sample from the stationary distribution, right? So I'll be using this notation again later on, so let me define it properly. Pi of m is the sum of elements in m from the stationary distribution of these elements. Right? So it's kind of the stationary probability of this set, right? If you have 2 vertices here, this would be 2 over n. And so indeed, since, you know, in every step you're effectively sampling from pi, you know, what's going to be the hitting time? You have success probability pi of m to sample marked element in one step. And the next step is kind of IID. So overall, you need something 1 over pi of m random walk steps to sample a marked element. Okay. Is that okay so far? Yes. I mean, it depends also on if you add the self loops, and so it's going to be, you know, I think at most 2 n over m or something. It's not going to be equal.
Simon, what here? Bottom of front right.
Who are you? Yeah.
Yeah. Hey, nice to meet you. Is that why? How did we use that? It was the complete graph for this last expression.
For this one?
Yeah, the one with 1 over pi of m.
Because what we're using, and in fact, that's a good question because it leads into, you know, so the next thing I'm going to say is that after every step, you're kind of redrawing a sample from the stationary distribution. And okay, so let me be precise about this, because I guess that's why you're asking. Like, in fact, this is a stationary distribution, right? So in that sense, you know, if you start in pi, then the next step, if you just do random walk step, you're again in pi. So in that sense, you could interpret for any graph at all, like even this cycle, that every x is a sample from pi. And this is true, but they're not IID samples. And that is precisely the distinction. It is a bit of a subtle thing, right? Here, you effectively jump in a single step to any other place on the graph, right? So you're effectively kind of forgetting where you were, and you know, but here this is not at all the case, right? In a single step, you just jump to one of its neighbors. So you're exactly, you know, or it's still at the same place where you started, more or less. And this is a bit in tension with saying that indeed after a single step, I'm still distributed according to pi, but it's about dependence, right? There's going to be dependencies, and in fact, okay. So that brings me to this lemma that I want to state here, which is that the hitting time of a set M for any graph at all will be of the order 1 over delta times 1 over pi of m. So we see that this pans out for the complete graph, right? We get the exact same expression, but it doesn't for the cycle, for instance. So this is a lemma, and it's not so easy to prove. It's kind of easy to prove it with log factors, but without logs, it's not so easy to prove. As yeah, I worked on this a little bit with the students, so he knows. Okay, in our case, we also know that this is order 1 over delta n over m, right? Because we're assuming that we have a regular graph, and so pi is the uniform distribution. Okay, So rather than this, which you would expect, maybe if you're saying that every sample, every point is sampled according to pi, you get this thing. So try to parse that for a second, and maybe if somebody has some intuition about why this would be a bound on the hitting time, please speak up. So does anybody have a guess, maybe? They can. They can help a little bit in getting the right picture. So what you want to do is you want to imagine that you have this sort of timeline here where you have an initial sample, an initial point, x0 is drawn according to pi, right? And then what we've just been arguing is that, in fact, if you look at the timeline, then also x1 would be distributed according to pi, right? So we know that in this initial step, even just our initial sample could already be in the marked elements, right? It could already be done. So this happens with, so this will be in M with probability pi of M. Okay. Now, can we make the same claim about this second point? Like imagine that kind of mark these elements here, and you start here. Just kind of got bad luck, and you're kind of on completely the opposite side of the graph. So can you say that if the first one was not in the set, the second one might as well be in the set again? It cannot. Because the problem is dependencies, right? That's what I was just talking about, that these are both samples from pi, but they are not independent samples. So if you got unlucky with the first one, then there might be a very strong correlation. You'll be unlucky with the next one as well, just as what happens on the cycle. But if we do the following, namely, if we wait long enough, and we look at x1 over delta instead, so we have the same claim. This will still be distributed according to pi. But because we kind of completely mixed up again, we can say that these are now IID samples. So essentially, right, I'm kind of ignoring some epsilons and deltas here, but these are effectively independent samples from the stationary, right? And this is really the correct picture, right? Because you want to somehow say, okay, I got unlucky, I got some bad luck at the start, and now I want to retry. But I want to kind of get away from my initial point as fast as, as far as possible. So you kind of just take this large number of steps so that, you're again effectively distributed according to the stationary distribution, even conditioned on what your initial point was, right? And so that means that after these 1 over delta steps, we can kind of say that now again, we are distributed according to pi, but in an independent fashion, and we again get this sample from the stationary, and we can again get lucky with probability pi of M. And now if you kind of pull this argument through, you can say that every 1 over delta random walk steps, you get an independent sample from pi. And then how many samples do you need? You exactly need 1 over pi of M independent samples, right? Yes.
So is this a bound on the, okay, so because it seems to suggest that it doesn't depend on the spatial distribution of the sites, but
no, exactly,
should, right?
So it is a bound, and sometimes it works well, like for the complete graph, and there's many more graphs you can think of. But for instance, for the cycle, and this is a bit sad, but even for the cycle, it is not a very good bound, because in fact, what you can show is, after 1 over n squared steps, you're kind of mixed, but somehow to mix, you kind of have to pass through all the vertices, right? Like, you know, if you don't want to pass through this one, it becomes difficult to kind of, so there the actual heading time is n squared. And this bound would give you n cubed. So it is an upper bound, but there's, you know, so a very clear intuition here, and we'll be using that to talk about quantum walk search. So is there any questions about this part at this point? Yes.
I could not quite understand why at this time 1 over delta, it will again be back to this uniform distribution.
Okay, so let's say that the problem here is that this is no longer distributed according to pi if we condition on, you know, having seen the first x0, right? If we condition on the first one, then this won't be distributed according to pi anymore, but this one should be, because whatever we did condition on, whatever initial vertex we kind of are conditioning on, we know that after approximately 1 over delta steps, we must be distributed according to pi again, just because of the definition of the mixing time. We are effectively mixing, right? And this point should, this exactly the thing with mixing should not at all depend on whatever, you know, you started from. So what your previous sample was. Any other questions? Okay, if not, let me just see this as an algorithm now. This is going to be 2 more lines, and then we can take a bit of a break. So what's the cost of this algorithm? So you can think about this as an algorithm for finding a marked element on a graph, right? Which sounds a bit abstract and boring, but in fact, there's many situations, even classically, where we'd actually, you know, like to do that. Ronald talked about something like Schoening's algorithm for tree set, where you also can follow a random path. Actually talked about these sort of backtracking algorithms, where also you can use random walks. So it's not as abstract as it sounds. And we want to actually go and quantify the algorithmic cost of this algorithm. So how do we do that? We look at what we're asking for, right? What are we asking for to start with? We're asking that we start from the stationary distribution. So this is what we call the sort of setup cost, right? And the setup cost is, non-surprisingly, the cost of setting up the initial point of our walk. So that means you want to sample x0 from the stationary distribution pi, right? So you can think about it, if you want, as if you're preparing the probability distribution pi. Okay. And then what we're going to do is we're going to take random walk steps, right? It's going to be one thing that we're doing, like we jump to a random neighbor, and this might sound trivial, but in many cases it's not trivial, it's a non-trivial cost. So we do that, we jump to a random neighbor, and this is what we call an update. And we should do one more thing. We should check whether we're at a marked element or not, right? And these are 2 different costs. So it's a bit like Ronald was talking about Grover's algorithm, where you have a cost of, you know, checking whether a certain bit string or state is a good state or a marked state or not. Here it exactly amounts to saying, if I give you X, is it an M or not? Okay. So I'm going to kind of abstractly quantify these costs. And then the thing is that what we can do, what's kind of nice about this, so indeed it's not a tight bound, but we can do the following thing. We can say that we only ever check after 1 over delta steps, because we're kind of going to go on a hunch and say that if we didn't get it here, then we're probably kind of in a bad place. And so let's just walk around a bit and not check, you know, because we're kind of probably far away from the marked set. So what's the total cost that you get that way? You get that you only check, you know, every 1 over delta steps, and you're going to run this for 1 over delta times 1 over pi m steps, right? So the number of checks will just be 1 over pi m or n over m, right? Denoted here. But the number of updates, like the effective number of steps that we're taking, will be this full expression, right? It's the effective number of random walk steps that we take. And so the update will be, this is not the most pedagogic way how I presented it. So in fact, let's go over it again. This is the cost of sampling this initial vertex. This is the cost of checking. Then you want to check, is X in M or not? And this is the cost of one random walk step. Okay. And you see that the total number of random walk, so we start from this pi, the total number of random walk steps is 1 over delta times n over m, because this is the hitting time. This is really like the, sort of the point on the axis where we'll actually find a marked element. And then, you could say that we check at every step, but that would be more costly. So instead, we just check every 1 over delta step, because then we know we actually get an IID sample. And that's why we just check this n over m times. Does that make sense? Sort of. Okay, so, okay. So this is the cost of what you'd call a random walk search algorithm. But it's at least, we have upper bounding the cost of a random walk search algorithm. I think we can take a break of 5 minutes and then continue and do quantum walks. Okay. Hi. So we just agreed to go for another half an hour or something, so until 22:11. I think things were going to move faster, but as it goes on a Friday morning, they did not. So, okay, let's still try to cover essentially, what we want to do, right? So we looked at this random walk search, and now I want to briefly recall Grover's search. It's going to help us, and it's also going to be an interesting sort of parallel to this random walk search cost, right? So let me just recollect Grover. So in Grover, we have this initial state, which now I'm going to call, and again, this is also why I kind of wanted everything to be regular and so on, so that I can call the uniform superposition that Grover starts in with a quantum encoding of a random walk stationary distribution. So we have this, okay? So the initial state of Grover, like we have the search space of n elements, and we have some initial state, which is the uniform superposition, and a Grover iteration. How does it look? So I'm going to ask you because, of course, you know now. So it consists of two reflections, one of which is a reflection around the initial state, around the, let's call it, a sort of stationary state. And the other one is a reflection around the marked elements, right? So this is what, you've been going through this week. And what we know is that combining these things, we kind of find a marked element after order root n over m iterations, the Grover iterations. Okay, so that's the algorithm. We're kind of assuming that we know m, but again, as Ronald mentioned, you can kind of deal with it even without knowing m. And let's look at the total cost of this thing, right?
Sorry, Simon,
Yes.
should the two reflections be reversed? Like the way I presented it, you first do the query and then the reflection around the uniform
Yeah,
state.
I think you could reverse them.
Makes no
But
difference.
I mean, this is going to be the identity operator on the initial state.
Oh, I see. Okay.
Right? I think I do it that way because it's closer to how we do it with.
Okay. And another possible point of confusion that what you call X is not what I call X. Just so that students are not confused about this. You can keep calling it X. I just wanted to point out
That's
it's different.
much worse now.
No, you can keep calling it X. I just wanted to point out that students shouldn't be confused.
No, okay, thank you. So it might become X again at a later point. Okay.
Now it's called blob, black blot of ink. So
Potato.
no, but it's not a joke. You can read it. I can't. It's an I, or what is it?
Okay, let's make it X again. So it's an X.
All right.
Okay. So what's the cost of this thing? Similar to, sort of the mental picture of what was there. There was the setup cost of creating this initial state, but then it was pi, now it's cat pi. So we're gonna have this setup cost. And I'm going to denote by the same as okay, here it's a sort of quantum setup cost. So we want to create this quantum superposition, which by no means is as easy as preparing the class. Like you understand it should be strictly harder, right? Because you can always measure it and then you get the classical sample. Or it should be at least as hard. And in many cases, in fact, it's harder, but in many cases it actually works and we can get nice things from it. So we quantify this by a non-trivial cost S, and then we have square root n over m iterations. So I'm going to hide big O here. I'm just going to write square root n over m iterations. And what's the cost of a single iteration? We want to do a check again. So recall from, I think also Ronald covered this, that you can implement this reflection by sort of, the main cost is checking if an element is marked or not. And then just some elementary gates to apply. So essentially, implementing this thing is one check. Implementing this thing is more non-trivial. So I'll quantify it as, R pi, the cost of, okay, so this is the cost for one iteration, right? And this here is the cost for the cost of implementing this reflection. So I already mentioned that setting up this quantum superposition is a non-trivial thing. But with that cost, if you have some unitary that sets it up, I think this was also covered, you can not only prepare the state, but you can also reflect around it, right? So we could kind of say like, okay, R pi is like of the order of S. And indeed is upper bounded by that, assuming some technicalities, but as it turns out, there's actually a much easier way to do it. Like in some cases, you can actually gain a lot by doing this in a different manner. And this is precisely where, quantum walks pop up. So here, we're going to use quantum walks. Okay, so we're going to use quantum walks to implement that reflection, and then we'll have a quantum walk search algorithm. But really, you can think about it as it's Grover, but one of its building blocks, we're kind of using something else to do that more efficiently. Okay, good so far? Okay. So.
Sorry.
Yes.
Yeah, I just realized that. So this multiplication between square root of n over m and the check. Somehow I thought that with Grover, it's more like, you basically, you have access to this, to the oracle that would allow you to do this reflections, essentially, 2 pi minus 1, right? Or rather, no, 2 pi m minus 1. But then you perform all these essentially rotations, and then after that you're almost sure that actually you're in the right point, and then you can check. But that would be like an additive rather than multiplicative. You don't have to check every time you. So
okay, but maybe there's a subtle point. Like we're not checking by measuring the state and looking, how did we do so far, and actually doing measurement. We don't do that. We just want to reflect around the marked elements, but obviously, this is going to depend on the marked elements, right? So if there's in some sense, it's hard to check if an element is marked, then somehow this cost should show up in reflecting around these elements as well, right?
So the cost of checking is there because you need to implement this 2 pi m.
Exactly.
Okay, cool.
Yeah. So you can do it exactly with the cost of classically checking in some sense if X is an M or not. Okay, any other questions? Okay, if not, then let's do quantum walks. So Okay, so imagine you're, at a vertex, and this vertex is called X, and then you have a bunch of neighbors, right? And then call neighbors Y. Okay, they don't have nice names for the things. That's Ursula and Wigner. It's just X and Y. So, what does a random walk do? It goes from, let's assume that we started in this vertex X, right? So P0 is, and now I'm gonna go completely out of it, and now I'm gonna use it. And it's like the indicator on X, so it's just, probability distribution localized on this vertex X. So you could have written cat X, but I think that would have made it completely impossible. So let's do then, we do P, we apply P to P0, and what happens, our distribution is now uniform over the neighbors of X, right? We jump to a random neighbor. So after one step, one step of a random walk kind of looks like this. We map this EX to this uniform mixture of neighbors. So Y tilde X means Y is a neighbor of X, and with EY, okay? So we just jump to a uniformly random neighbor. Our initial distribution was localized on X. The new distribution is kind of uniform over the neighbors of X, okay? Now we have that. This is like the building block of random walks. Now let's try to make a quantum walk from that, right? And in fact, it's not as easy as it sounds. One of the problems I already mentioned was that a random walk kind of forgets where it started, right? It's kind of intrinsic, like in doing the stochastic or dissipative dynamics, if you want. You're going to forget and you're going to converge to the station wherever you started, right? Now, quantumly, we cannot do that. And so in that sense, like the naive thing would be to kind of go from X to superposition of the neighbors of X. But what if you're in a situation like this, like you have some X, it has a bunch of neighbors, but now there's another vertex that has the same neighbors, Z, for instance, right? Then you would like to map X to uniform distribution over uniform superposition over neighbors, but you would like to map Z to the same thing, and you can't do that because of unitary dynamics. You cannot map two states to the same state. So it's not quite as easy as that, and it sounds like a futility, but it is not. And people struggled for a long time to kind of, how do you define quantum walks? What's the right way to do it? And in fact, there's not as clean and crisp a definition as there is for random walks. And that's a bit sad, but it is, how it is. But what we can do at least is, because now we know that this exists, we can look at it as a block encoding. And this is kind of a new way of looking at it. So people are in the dark for quite a while on how to define quantum walks. And then someone kind of just cooked up the right picture. And now we understand that, in fact, you can think about this as a block encoding. So how do we define a quantum walk? So again, like I said, there's many definitions, and in the literature, you'll encounter many definitions. But here, we'll define it as a block encoding. So this is a C, as a block encoding of the random walk matrix. Right, and it kind of makes a little sense, right? Because you want to sort of start from this P and then construct a quantum object from that. That's like close to P in some sense. Maybe I can fit it on this board. So how do we construct the block encoding of P? The people that were there on Tuesday, we did this exercise in constructing a block encoding. So you can doze off for a second, because it's exactly that I'm going to briefly explain here. Namely, how do we construct this block encoding? We have two things here. One is what we call a row oracle. And this is much more like what we would have expected that we would be doing here as a sort of naive quantum walk approach, right? So a row oracle V for P. So this is really like a linear algebraic thing, it's you create this quantum state corresponding to a row, but then we'll kind of see that it's essentially like, sort of naive thing that you would have done here. Namely, what it does is, see, you have some psi 0 of the form, psi 0 is equal to 0x, so x is the vertex, and we have this extra register here, right? So we call block encodings, you kind of have to blow up the state space a little bit, and we map this to V. C0, so V is this row oracle that we have for P, and V will kind of, squeeze in P in the quantum state. So precisely how does that happen? It looks as follows. We do exactly what we would have wanted to do in the first place. We turn the first register into a uniform superposition of the neighbors of X. And you can think about it as doing sort of a quantum version of a random walk step, or you can think about it as a linear algebraic oracle that just maps this 0 to the xth row of P, right? You could define this for general matrices. But now who sees why this we can do, whereas, you know, this thing here we could not do? Yes.
What does the perspective of the block encoding gain us here in this picture? I mean, if you would just want to take a superposition over neighbors and make that uniform, wouldn't this also already be kind of a canonical mapping that you would do?
Yeah, but okay, so again, let me spell it out here. Like naively, we would have wanted to do this, right? 1 over square root d neighbors of X, Y, but we would have wanted to map, you know, Z to the same thing, right? And we can't do that.
The same way that we like do a normal query, you would then also keep another register with kind of saves.
Exactly.
What you're doing.
So yes, so this was supposed to be the question, right? And that's the answer, right? Because you keep an extra register, you can remember where you started from, and so X would get mapped to this state tensor X, Z would get mapped to the state tensor Z, and these are orthogonal states, so that's fine. But I guess that was not your question.
No, it's like this would have probably already been kind of thought of before block encodings to do this. So
yes.
Why do we do block encodings?
Exactly, but I'm not quite there yet. So this is, you know, this row oracle, and then we have this swap operator, which just does this. It maps X, Y to swap of X, Y, which is equal to Y, X. It just swaps the two registers. So really now you can think about the quantum walk step in some sense as you're at X. You kind of generate the superposition of neighbors in this extra register. This is, you're still at X. You just kind of generate the, you know, sort of direction, and then you'll actually make the step, like you actually flip, and you put Y in the sort of position register. And there was all these intuitions like that, and people were kind of, you know, struggling with that, because if you just do that, like this row oracle and then the swap, like things don't quite pan out yet. You want to do some, like, you want to have this slight extra twist, namely, you define your quantum walk operator as, so let's call it W as V dagger S V, right? So again, you imagine that you're at say, 0x, so you add vertex X, kind of generate a superposition over neighbors, you know, you do the swap, so you actually move to your neighbors, but then you have to do this V dagger as well. And I always thought it was a bit odd. Now, the first thing that we gain with block encoding is that this is exactly how you construct the block encoding, right? So you can actually, and this was in the exercises, then this works for essentially any matrix. You can see that this will be a block encoding of P, okay? Not only is the block encoding, it's also a good block encoding because if we apply this operator twice, what do we get? We get V dagger S V, V dagger S V, but these are unitary, so these cancel. Swap, swap is identity. If swapping twice is identity, and again, you get V dagger V, this also cancels. And so we see that we get a block encoding that's also a reflection. And this was kind of the well-behaved thing that we liked. Okay. Now, what do we gain by taking this picture? One thing is that now you define this as like, you know, let's say you don't even know that, right? You define it like that. So, you know, why is it good? You know, what can you do with it? By taking this, by understanding this is a block encoding, right? You kind of understand the construction a little bit, but also something that you can do now is you understand that if you apply this matrix, and we saw that just applying this, you know, twice you get the identity. So what we do instead is we add this reflection inside. You see, it's always about sort of reflections. And we put it in front of this quantum walk block encoding, we apply this k times. What do we get? We get the k Chebyshev polynomial of p. It's exactly what we saw on Tuesday. Also proved it to some extent on Tuesday. And this thing here is exactly the way quantum walks were, sort of canonically defined by Mario Szegedy in 04. So, we have this block encoding perspective, but this wasn't around at that time, right? It's just a way of constructing this quantum walk operator. Okay, and so, sorry about that. I didn't want to call this W. Now I understand why, because I want to call this W, but let's call this W prime then. This is how this quantum walk was defined, and now we can understand this as being one of the first examples of a block encoding, right? Okay, and it's 10:30, so let's see where we get. I think we can get there. So maybe I'll save questions for in 10. Or maybe we can do.
I actually have two questions. First question is why Z cannot be mapped just like the X was, and the second question is when W prime is in fact a reflection, why are you multiplying it with this reflection operator 1 minus 1?
This is well, I mean, you can do different reflections, right? And taking the product of different reflections, like in Grover, is interesting. You get a rotation, and you can actually get something out of it. Okay, maybe I'll. Is that okay for we can talk afterwards? Okay, so what you can do as a relatively simple exercise now is, but let's not do it now. You can see that if you start from the 0 with this pi state here, then you'll see that it's also an invariant state for our quantum walk. So this is not so hard to prove. Okay, so what we see is we construct that from this random walk, we construct this quantum walk, and we're already retrieving one key aspect of the random walk, which is the stationary, right? This quantum walk operator somehow has the right stationary as well, just the quantum encoding of that. Now, it's not going to be the unique one eigenvector W in general, but it's going to be the one that we care about. Like we're always going to stay inside the right subspace somehow. So we see that this is somehow sort of quantum walk stationary. Okay, good. So what does that mean again? It's not the unique eigenvalue 1 eigenvector, but for all practical purposes, of this thing, it is. And so we have this one eigenvector here, corresponding to pi, and then all the other ones, because it's a unitary, are just somewhere on the unit cycle as well, right? And now we recovered the stationary thing, like in the random walk. What was a different aspect that's important about random walks is the spectral gap, right? We see it kind of determines a lot of the thing that we want to do with it. So also here we define sort of this thing here as the spectral gap of the quantum walk, right? Kind of the gap around the eigenvalue that we care about, right? So this should be at least delta. Okay? But this implies that we can use quantum walks to reflect around pi. It doesn't apply directly, I'll explain why, but this is the gist of it. Like a quantum walk somehow in this pi vector here, in fact, there should be a 0 in front. The 0 pi vector is a sort of privileged, stationary vector of this quantum walk, and it's exactly what we'll be using. Because what we see is we can use this quantum walk operator to reflect around pi. And recall that is exactly what we wanted to do, right? It's exactly the operation that we want to do. And how do we do it? So for any ket psi, so this will be in Cn, so it's like over the vertices of the graph. You can decompose, and again, we don't do this explicitly and don't effectively do this in an algorithm, right? This is just like an analysis tool. We can decompose it into eigenvectors of the quantum walk, right? So again, we get some alpha 0, 0, pi, just like we did classically. But now you have also these sort of auxiliary modes if you want. So we have alpha j. I'm not sure what's there's a mic on. Alpha j, vj, right? And now vj is an eigenvector of w in the sense that w vj is equal to e I theta j vj, right? So we have some e I theta j here, and this corresponds to an eigenvector vj. Okay, so we can decompose initial state like this into eigenvectors of the quantum walk with this privileged one, you know, in the front, right? And we know that all these theta j's in absolute value are at least delta, right? There's kind of this gap around this eigenvalue 1. So 5 minutes. So what we can do is we can do quantum phase estimation, which is something that Seth talked about, to kind of distinguish this privileged eigenvector, this one, from the other ones, because this one has an eigenvalue 1 or a phase 0. These all have pretty large phases, right? All phases larger than delta. So what we do is we use quantum phase estimation, and I'll recall what it does. We denote it by Q, P, E, and it does the following thing, right? We take some initial state, like 0 psi, but now we add an extra register. Like this extra register is going to be where we kind of put the estimate of our eigenvalue. So what quantum phase estimation does is it maps this to, so we could decompose it like that. So I probably should have written that instead. We, like this first one, you know, corresponding to the 0 or the 1 eigenvector, we'll get a 0 here. This is our estimate of the phase, if you want, right? Like the, you know, 1 is equal to e I 0, right? The phase is 0 here. But the other ones, you know, we get the sum alpha j vj. And here we'll get an, you know, if we do it properly, this quantum phase estimation, we get a non-zero estimate, right? Because these eigenvectors have a non-zero eigenphase. I mean, they have an eigenvalue of the form e to the I theta j. And so in fact, what we'll get here is we'll get some estimate theta j tilde. It is not going to be precise, you know, you do quantum phase estimation with a certain resolution. But if we do it with the right resolution, in fact, I'll, you know, add it here as a subscript, QP subscript delta, which just means that we do it with resolution delta, which is exactly what we need, right? To distinguish this one from this one. And so this one is a delta estimate of theta j, okay? And since we picked the resolution in such a way that, you know, this will be non-zero, we see that this will be the only part of the quantum state that actually has a 0 in this estimation register, right? So what we can do now is we can, so let me write it down, but it's a bit long, so we can kind of, in words, it's easier. In words, we just look at this register. If there's a 0, we leave it be. If there's something else in a 0, we add a minus sign. So that effectively, and this is an operation that is what we call elementary, right? It doesn't, you know, depend on the quantum walk. It doesn't depend on anything of the input. It's just like an elementary operator, just looks at the register and adds a minus or a plus. So we get the same thing, except that here we get a minus sign, right? And why do we want to do that? Precisely because we want to reflect around the pi state, right? So we want this one to stay invariant, but we want to flip the sign of all the other perpendicular states. So now if we do this, sort of uncompute this, there's always a subtlety, but you want to kind of get rid of this again. You go back to, you know, alpha 0, 0, pi 0 minus some alpha j vj 0. But this here is precisely equal to 2 pi minus identity. Okay, so I'm being a little bit sloppy here. It should be pi and 0, but then it's going to be a bit ugly. But essentially, it's a reflection around the stationary one applied to our initial state 0 psi, and then we have the extra phase estimation register, which you can kind of ignore again. Okay, so what we did is by using this quantum phase estimation, we kind of implemented this reflection. So this is not exact. It's so I'm hiding the epsilon delta strip, but this is the gist of it. And the key is somehow that the resolution, if this gap is larger, they can do it with a worse resolution. But if delta is small, you need a better resolution to kind of distinguish the one eigenvector from the ones close to it. So the delta shows up in here, and this is exactly, sort of the cost of the thing, right? What you can show is that this requires something like 1 over delta quantum walk steps. And this is great because now we see that effectively, putting a lot under the rug, but effectively we can do this reflection in 1 over delta quantum walk steps, where delta is now the big delta, the gap of the quantum walk. Okay, and then we're almost there because now we can kind of quantify the cost of this thing here, right? We can replace this reflection cost by 1 over delta quantum walk steps, right? So the quantum walk search cost becomes the following. We have a similar setup. We have a similar root here, n over m, and we have a checking cost, but then we do this reflection using 1 over delta quantum walk steps, and one quantum walk step is like one random walk step. We denote it by u, like the update cost. So we get 1 over delta u. This is the cost of a quantum walk search algorithm, but we're not quite there because the question is now, what is this delta here? Right, and this is the last thing that I'm going to say, and this is sort of the magic of it. This does not just follow from blocking. In fact, this follows from the earlier thing that Mario Segedi did when he defined this quantum walk. He actually, people asked me what's in the don't care blocks in the block encoding, and he looked at that. It wasn't called a block. He couldn't just put dots there at that point. So he kind of analyzed the full thing. He proved what the spectrum is of it, and something very magic happens. Recall that your random walk eigenvalues look like this, right? This is like sigma of p. And what he proved is that these get, I want to give you this because it's really a bit magic. So what happens is that exactly what you would like it to do. Each of these eigenvalues gets somehow magically mapped to the unit circle, right? I mean, what else, right? So this is what happens, and once you have this picture, you see that if there was a delta here, then this gets mapped to the unit circle, and by just doing some goniometry, you'll see that this implies that this will scale as square root delta. In fact, what you can show is that this will be scaling as the square root of the delta, and this is I think this is magic, but that will conclude it because then we get that this here is essentially S plus root n over m, C plus 1 over root delta u, and we get exactly we're exactly putting square roots over the cost of random walk search, right? So that's it. I'll stop here and thank you.